Hello. This is Nicholas, and today I'm going to be doing a video on the second partial derivative test. And so this will generalize the techniques from single variable calculus, where we found local maximums and minimums of single variable functions, to those with two variables. In other words, functions of the form z equals f of x comma y, like how I have written there. So in Calc 1, just some refresher here, we found where the tangent line to that original function was horizontal, and then we tested concavity to see whether concavity was positive or negative, and then from there we could determine a local maximum or local minimum. Here we will somewhat be extending this. There will be some changes because we are dealing with a multivariable function, and so therefore there are infinitely many directions to approach our point that we want to test. The point that we want to test will be called AB. So first of all, critical points. In Calc 1, we just set the derivative equal to 0, and we call that a critical point. So it's a similar idea here. We set the partial derivatives, all the partial derivatives, which in the two variable case is just f sub x and f sub y, and we set these both equal to 0. If you do that, and you recall the equation for a tangent plane, our equation for our tangent plane would then just be z equals f of a comma b, which is a horizontal tangent plane, and so we would it would make sense there that at that point there would be something happening, a local maximum or a local minimum, something like that. So instead of just taking the second derivatives, though, there's only one. We're assuming the functions are continuous, so there would only be one mixed second partial derivative, right, by Clairaut's theorem. But here what we need to do is we need to introduce this new differential operator D. And so the reason why we need to introduce this is because to approach the point A comma B and test it for a local maximum or local minimum, there are infinitely many directions that we could approach it from, right? We could approach like along a parabola, along a linear function, along a horizontal, a vertical function, infinitely many ways. So testing concavity won't be that easy because you might have things like saddle points where concavity is positive in one direction but negative in the other. So we introduce this new differential operator D, and it's defined like this. So our differential operator D is a function of x and y, and it's f sub x of xy, f sub y of xy, minus f sub xy of xy squared. Now, in the next video, I will give proof and motivation for why this D is what it is and where it comes from. It turns out, actually, that if you want to maybe do some research on your own, this is actually just a special case of what's known as the 2x2 Hessian matrix. And so if you were to generalize this to like functions of, find the maximums and minimums of functions of like n independent variables, you would end up using what's called the Hessian matrix. And you can find that all over the place. So now the idea here is that this is like sort of our new concavity test. This new differential operator D is like our new concavity test. So it follows similar rules like to Calc 1. So for example, if D of x comma y is greater than 0, and we'll say f sub xx of xy is greater than 0, then f of xy is a local minimum. It's a local minimum because see here we have our concavity test being positive, and then we have we have this situation where we have our graph. Maybe this is like a cross section on 2D. It would be doing something like this. So our concavity is positive in this type of graph, which is shown here and here. But then we have also the positive concavity from here, so that would mean a local minimum like right here. So Notice that this D operator kind of fights between like concavity purely in the x direction and purely like concavity purely in one direction here versus concavity that is in both directions. So if this here, when we square it, is bigger than what we see here, then we're going to have a problem. And also, if this is negative, if this is negative at all, then we're going to get a negative number here for sure. And so what that would mean is that if this is negative, then we would be having directions where we approached, if we approached from one direction, we would get, say, positive concavity. And if we approach from another direction, we would get negative concavity. Because definition of concavity, if, say, you have positive concavity along the x direction, but negative concavity along the y direction, this is going to give a negative number, and then therefore this whole thing's going to be negative. And so therefore we would have a saddle point. So this is a necessary condition, and this is a necessary condition. Now note also that here I could have used f sub y of xy instead. I'm writing it in laser on purpose, but because it doesn't really matter which one of them I use, I'm just verifying that the concavity in whichever direction I choose is positive, and so therefore I would have a local minimum. Okay, and then that's the first possibility. The second possibility is if we have d of xy still being greater than 0, and we have f sub yy, or I used f sub xx up there, so I'll use it again down here, and we have f sub xx of xy being less than 0. Then we would say, similar reasoning, f of xy is a local max. So that would be something where we have this type of situation, right? Because this implies a negative concavity. So the third situation is if d of xy is less than 0 and f sub xx of xy is anything, it could be positive or negative, then f of xy is a saddle point. And so a saddle point is a point where if you approach along one direction, you get positive concavity, whereas if you approach along some other direction, you get negative concavity, and so you can't really say whether it's local maximum or minimum. And it looks like a saddle, right? If you've ever seen a saddle in your life before, if you like go along it horizontally, it's got like a negative concavity, but if you go along it vertically, it's got a positive concavity. And so that's why we call them saddle points. So now the reason why we need to make sure for these first two conditions that the d of xy is greater than 0 both times is because we need to make sure that basically concavity is matching up. So we need to make sure that concavity in the x direction and concavity in the y direction are matching up, because if they aren't, then we're going to have a saddle point. But if they are, then we just need to see, okay, is that concavity positive or is it negative? And then from there we can determine a local maximum or a local minimum. And just like here, we could have replaced we could have replaced this with f sub yy of xy or f sub yy with xy. It doesn't really matter which one you choose. You're going to have to compute all of them anyways. So I guess whichever one's easier to plug into. Okay, so let's do an example here. So let's say we have f of xy being x to the fourth plus y to the fourth minus 4xy plus 2. And this function is a continuous function because it's just a polynomial, a linear combination of polynomials. So the first thing that we need to do from this second partial derivatives test is we need to find f sub x, or f the partial of f with respect to x, the partial of f with respect to y, we need to set both of those equal to 0 and solve that system of equations to get our critical points. So f sub x is going to be 4x cubed minus 4y, and f sub y is going to be equal to 4y cubed minus 4x. And we're going to set both of these equal to 0. What this implies is that y is equal to x cubed and x is equal to y cubed. So I think what I'll do is I'll plug this into here. So if x is equal to y cubed and y is equal to x cubed, then I get x is equal to x cubed cubed, or x to the 9th. And that's still going to become x to the 9th minus x equals 0. And so x times x to the 8th minus 1 equals 0. And what this factors into is, we would get a lot, actually. Let me write it all out, I guess. Well, first we'd get x times x to the 4th plus 1. That has no real roots. And then we'd have an x to the 4th minus 1. But x to the 4th minus 1 is x squared plus 1 times x squared minus 1. So we'd have an x squared plus 1. And then we'd have an x squared minus 1, which is x plus 1 times x minus 1 equals 0. This and this have no real roots. So under the reals here, which is what we're considering, we can just get rid of and ignore these factors. So that means we have the critical points with x coordinates x equals 0, 1, and negative 1. So now, since y is just x cubed, right, from this here, if y is just x cubed, then we can just cube each one of these to get the corresponding y value. So y is 0 cubed, which is 0, 1 cubed, which is 1, and negative 1 cubed, which is still negative 1. So our three critical points that we need to test are 0, 0, comma 1, 1, comma negative 1, comma negative 1. So now we need to find, from here, we need to find f sub xx, f sub xy, and f sub yy. So f sub xx is taking this again with respect to x. So we just get 12x squared. We need to find f sub yy. That's taking this with respect to y again. That's 12y squared. And then f sub xy, or f sub yx, it doesn't matter because they're the same because the function's continuous. So Clairaut's theorem applies. Let's say I do this here with respect to y. With respect to y, I just get a negative 4. And you can see that if I did this with respect to x, I would also get a negative 4. So they are indeed the same. So then our operator D is going to be 12x squared times 12y squared minus 4 squared. So that's going to give us 144 x squared y squared minus 16. Okay, so now what we need to do here is we need to plug 0, 0, 1, 1, and negative 1, negative 1 into this. So d of 0, 0, that's just going to be negative 16. D of 1, 1 is, we don't need to know what the exact number is, but it's going to be positive. Let's just leave it at that. That's all we need to know, positive. And then d of negative 1, negative 1 is going to be the exact same number, and it's also going to be positive. So now what does that mean? It means that we just need to find what the concavity of, we just need to test, well, we don't even need to test 0, 0 because we know right away that since d of 0, 0 is negative, this is a saddle point. So we don't even need to test that. We just need to test it for, we need to find f sub xx evaluated at 1, 1, and f sub xx evaluated at -1, -1. And so when we plug either of those in, we get something that's positive in both cases. And so what that means is that, in these two cases here, we have this type of situation where we have positive concavity. So that means we have like a local min here. So in all, we know that 0, 0 is a saddle point. We know that 1, 1 and -1, -1 are local minimums of this function. And so that would take care of that example. One other thing I would just like to note is that you can remember this D operator a little easier because it's actually the determinant of the following 2x2 Hessian matrix. It's f sub xx, f sub xy, f sub yx, and f sub yy. And notice that f sub x, when you multiply along this row and subtract, f sub xy and f sub yx will be equal by Clairaut's theorem. So you don't need to worry about making them separate. You can just square f sub xy. Or you could square f sub yx. It's the same thing. Okay, maybe just one more example here. So if we have f of xy being e to the x times the cosine of y. So we first need to find f sub x. F sub x is just e to the x cosine y. F sub y is going to be negative e to the x times the sine of y. And both of these are going to be set equal to 0. So what I can then say, since these are both equal to 0, then they're both equal to each other by the transitive property of equality. So e to the x cosine of y is equal to negative e to the x times the sine of y. And normally you can't divide by a variable, but since e to the x is always positive for the real numbers, which is only what we're considering, we can just cancel out an e to the x since it's always greater than 0. And so we get that the negative of the tangent of y is equal to 1 there. And so the tangent of y would be equal to -1. And so where does this happen? Well, it happens when the doesn't it happen at negative pi over 4? Yeah. Negative pi over 4. So if we just restrict our y from, say, the fundamental period of tangent, so y will be an element from negative pi over 2 to pi over 2, then what we can say is that there will be the y value of our critical point. But the problem is that then we would have something like this. We would have, if we plug into the first one here, if y is negative pi over 4, cosine of negative pi over 4 is root 2 over 2. And so you would get e to the x is equal to, if you plugged root 2 over 2 for here, and then you divided, you would get something that's negative. And so in other words, it wouldn't be possible. So this function here, and also if you were to plug into here, you would get e to the x is equal, I'm sorry, my bad. Let me write it out. In the first case, it is possible because you have e to the x root 2 over 2 is equal to 0, and so then e to the x is 2 over root 2, and that's possible because that's a positive number. But in the second case here, you'd have e to the x is equal to negative 2 over root 2, and that is not possible under the reals. And so what that implies is that this whole thing will not have a local maximum or local minimum or a saddle point because there are no solutions to this original. There's no critical points to this function here. So one other thing I would just like to mention is that if the D operator here is equal to 0, so if D of x comma y is equal to 0, then what that means is that the test is inconclusive, similar to how, not for the same reasons, but like how when you have the ratio test to determine whether a series converges or diverges, and you get that the ratio is exactly equal to 1, that's like hanging right on the balance between whether it's going to be a converging geometric series or whether it's not. And so you need to do more things with it. It's similar situation here, right? It's hanging right on the balance of whether there is differing concavity depending upon the direction that you change in. So, or the direction in which you approach the function at. So, in other words, you need to do more work there if you get the differential operator is equal to 0. Just like how with series you would need to do more work as well. I think that takes care of this video, and in the next video I will prove this second derivatives test in a much more rigorous way rather than just blindly following me. I want you to see why it's true as well.